Так, всем привет. Скажите, как меня слышно, видно? Надеюсь, кто-то в трансляцию подключился. Привет, человек, привет, Турбо. Надеюсь, вы все еще здесь. Так, значит, тема сегодняшнего нашего разговора, как уже вы видели по превьюшке, по принтскрину, это алгоритм Double-Dabble. Значит, это мы продолжаем серию серию стримов по реализации различных алгоритмов на ПЛИС. Вот, в прошлый раз мы разбирали алгоритм Луна и алгоритм Верхофа. Алгоритм Луны я сделал и статью на Хабре, алгоритм Верхофа пока лежит в виде стрима только. И сегодня, собственно, как я планировал, сделаем алгоритм Double-Dabble. Значит, сегодня мы сразу посмотрим, что это за алгоритм, для чего он нужен. В целом, с этим алгоритмом вы сталкивались абсолютно 100%, когда пытались реализовать, ну, скажем так, в неявном виде, да, когда пытались реализовать подключение семисегментных индикаторов, например, да, или часов каких-то. Круг мелкий, не надо на это обращать внимание. Привет, Саймон. Ничего страшного. Так, значит, неявно с этим алгоритмом сталкивались, когда пытались реализовать что-то на семисегментных индикаторах, да, то есть мы когда переводили из формата представления числа в формат семисегментного индикатора, мы, скорее всего, использовали так называемое представление BCD, binary coded decimal, да, то есть это мы фактически вводили цифры. Собственно, когда я занялся изучением вот этих вот алгоритмов Луна, алгоритмов там различных, у меня возникло непонимание, как я буду представлять. Okay, Ahmed asked us to switch in English. Hello, Ahmed. Okay, thanks for joining. Guys, we will switch in English. So Ahmed asked, so we could switch. So when I did a algorithm, first of all, sorry for my English. Okay, I'm not a good speaker in English, so but it will be interesting experiment for me in preparing for future seminar in Taiwan. We'll go in English the stream. So Double-Dabble algorithm is a next step for from sets of streams on YouTube. In previous time I tried to release. Yes, hello Meyer. In last few streams I did Loon algorithm and the Verhoff algorithm. So they are available on GitHub. They are available on as an article on Hubbard.com. So you could find it. And today, as I planned previously, I would to try implement Double-Dabble algorithm. It's also named as Shift and Add 3. So this is a very famous algorithm, so which everyone used previously when we was just in the beginners on FPGAs, when we tried to implement some specific digit indicators using seven segments displays. So what is an idea of this algorithm? So hello Krishna. So what's in the main idea? So we have some binary number. Yes, for example, give me a second, I will open calculator. So we have some binary representation of a number. For example, as I did previously, it's for example 30. In binary, it looks like 001, 110, 1110. So, and how we could convert this 30 number in binary representation to two digits, to 3 and 0. So, to be able to do this, we know typically some specific representation of numbers as a binary coded decimal. Yes, it's a very famous representation. Give me a second, I will Google it. So it's just a binary code representation. So when we get some digits in in decimal and convert it to binary. So we have some specific tables how to convert it. It's just in the representation. So, but if it's very good if we have, it's very simple if we have some small number, for example, yes. But what if we have some number as the input, but which contains a lot of digits? For example, if our number will be for example, something like this. You see, it already contains 1, 2, 3, 4, 5, 6, 20, 24 bits, and it contains already 7 digits. So our main goal today is to convert this number or any number in binary representation two decimal digits 3194303 using specific algorithm. So its algorithm names as Double-Dabble. Give me a second. I will also Google it. So it's not Double-Dabble, or it's wrong link. Double-Dabble. So what's the main idea of this algorithm? This algorithm is really it's really simple. So it's not difficult to for implementation. And the idea of this algorithm is really genius. So what is the main idea for today? So we get some representatives of number in binary. Okay, any number. It could be any number, and we need to convert it to decimals, to digits. Yes, as I told before. For example, this number we have in binary, and we need to convert it to these sets of digits. So, and what's the idea? Main idea. So, first of all, we need a number and some buffer where we will save our digits. Our digits will be from 0 to 9, so we will need just some sets of 4 bits buffers. The main idea of algorithm is just shift one by one this number and do additional with 3 when this number in any of buffer will be more than 4. I mean, if number in buffer will be 5, 6, 7, 8, 9, we need to add 3 and continue our shifting. Okay, it's very simple. So just shift and add 3. And as in this example, you see here is just an initialization. So initialization stage for this algorithm is always 0. So our buffers always will be 0. We give a number in binary representation. Doing first shift, we have a 1. 1 is less than 4. So we could continue shifting. We get 3. 3 is less than 4. Then we get a 7. Doing one shift more, and we will get a 7. 7 already is more than 4. So, and we need to add 3 to 7. So we will take a 10. Okay. Next step, we need to shift again. We're doing shifting, and now we will have 5 in first buffer. Okay. 5 is more than 4. Do addition with 3, we will take an 8. Doing shift again, here is a 3, here is a 0. Doing shift again, here we have 6, here we have a 0. So we need to add 3 to 6. We will take a 9. So now we need to shift again, 1, 2, 1. This number is less than 4, then doing shift again. So it's 2, 4, and 3. Zoom screen. Okay. So this is very easy. So very easy, very simple. I will, I will push this link to chat if you would to see this in future, and try to understand how it's working. So in internet, I found some different implementations of this algorithm, and most of them is containing some specific FSM, finite state machine. So in the finite state machine implementation, it's just a terrible, as I understood. It's not easy to understand the structure of this algorithm. It's not. It's will contain a lot of logics because, for example, Double-Dabble was, if I'm not mistaken, non-lab website. So yes, it's just another English-based community, non-land. If you know this guy, please subscribe to him on YouTube on his interesting lectures. So, and he suggested to organize it as PSM, and he puts all logic which should shift and doing additional with 3 in this FSM. So he will organize this a very big code. So with dramatically big expressions, and this code unfortunately not synthesizable. I don't know why, but this code produced an error when I tried to implement it in Vivado. So during the synthesis, here's some a basic misunderstanding of how to say in VHDL. So I don't know why some digits are assigned not correctly, and the range of variables going to outside or out range of, and variables was as out range, so it's incorrect range of variables. But when I check the code, just to understand what's happened, it was correct, but I don't know why Vivada not synthesize it. And I suggest today doing more bit another type of implementation and try to build a common structure which could help you to implement this algorithm for any numbers, binary numbers, and the representatives for specific digits. So it could be absolutely any number. You just will need add few parameters. It's just a num is which of binary number and how many digits you will expect in this in the endpoint. So what is the structure of this algorithm will be for us. I will open Draw.io as I doing always. Sir, can you brief once, because in starting it was in some other language. Oh, I repeat this what I said in Russian language. So it's the same what I said as was in the Russian language. So don't worry. You didn't mistake anything. So I will create a simple Draw.io diagram. Give me a second, I will save it. I will save it in a specific folder. This code will be uploaded on GitHub after stream. Double-Dabble. So what I suggest and what my idea how to implement this. So first of all, as we see from Wikipedia page, we need a number. First of all, it will be a binary number, and this binary number should in the future be presented as decimal number, decimal digits. So first of all, we will need some specific register which will save our number. So how we could suggest organized? We will have a specific register where we will put our initial binary number. So this will be just a shift register, simple shift register. Simple shift register. So next, what we will need some sets of temporary buffers, and these buffers will have one additional feature. So if the number which inside of this buffer is less than 4, then we need just a shift. If number is more than 4, we will need to add 3. So, and what I suggest to do, we will build some sets of such shift registers. Shift register 3 down to 0. So we will have some sets of shift registers, because we will need only 4 bits, because our digits couldn't be more than 9. From 0 to 9, it's enough to have 4 bits to save it. So in this shift register, every of these shift registers will have few ports. First port for it will be clock input. Give me a second. I think I will remove it. It should be clock input, because we will need our system will be synchronous with specific clock cycles, and this allows to us going through it will be synchronous system. So first of all, it will be clock signal. For next, we will need some reset signal. Why we will need a reset signal? Reset is required because this register should be resets every time when we need to calculate a new number, we will need to do a new conversion. So if we have if we complete computing one number, binary number, conversion one binary number to shift registers, to digital numbers, to digits, sorry. Then we will need to reset it, because these shift registers will contain old representation from other number, from previous number, and when from previous number. So, and it could be some situation when these registers will contain some old numbers, and this old number could be, I would say, will have some wrong values, and we will need to reset it, because zeros is the initial state of this. Next step, what we will need? We will need two signals like E shift, which will implement the shift of our bits in shift register, and we will need signal add. So signal EADD will implement going too high, and we will add this number. No, sorry, I mistake. EADD. Okay, let's say we will have it. Okay, and also we will need some output from our shift register. It will be OQ. It's just one bit output, which will connect to another shift register. Sorry. To another shift register, and we will need some output which will represent our digits. So it will be O digit 3 down to 0. So this will be our module. Okay. Hello, Женек. I did. So this will be inputs of our shift register, and so will be some digits. We will create this chain of shift registers using specific constructions in VHDL and Verilog, which names this generate statement. You know, we will create only one module, and will instantiate number of these modules depending from number of digits of our final representation. Oh, it's freeze. So guys, I think stream is down. Okay. Main idea is using generate statement to implement these sets of shift registers with function add and function shift. So algorithm has not determined latency, because number of add free and shifts, number of shifts we know how much we will do this. It's equal as a number of, it's equal of which of initial binary number, but how much adds we will need, we don't know. So, and I suggest one simple thing, doing sequentially shift and add. So we will shift. First of all, we will send the signal shift to this register. It will shift. Then we will send ADD pulse, and and then we'll decide inside of our shift register if our number is more than 4, we will do add with 3. If number is less than 4, equal or less than 4, then we will do nothing. So we will save the same number. This is a very simple idea. So that is the main idea. Also, we will need some specific finite state machine. It will be very simple. It will be main finite state machine. So which will just send few pulses to. It will control shift registers. It will send ADD. It will send to shift pulses. How to? Okay. So and we'll clear our shift registers after completing of computation. So we will firstly build this shift register, then we will build finite state machine, and then organize it as a simple project with a generate statement. So it's very easy. We will use initially VHDL language, and if we will have a time, I think we will have a time, I will convert it to Verilog. So the code will be almost the same for Verilog and VHDL, and the test bench also will be the same almost for VHDL and Verilog. So there are no, it's not difficult to implement it. Okay. So let's start. Hello, Artem. Let's start doing this with Vivado. So I will create a new project which names Double-Dabble. So nothing, we do not need to create anything. Our target FPGA will be XC7A35T ESG 3 to 4. It's a FPGA which installed on RT board from Digiland, but you could select absolutely any as you want. Yes, guys, if you have some questions, please ask it in chat, and you have some suggestions, also send them in chat. Do not send the links, because the links will not display in chat. I mean web links. So let's create new VHDL model, which be shift register. I will name it shift add free module. I can't. Sorry, I will remove it and create again. Shift add free. So I will save it in specific folder to be able immediately upload it on GitHub. It's cool, you speak in English. Yeah, sorry. Guys asked me to. I also posted this stream link in, let's say, in LinkedIn, and I sometimes asked guys, would they have a stream in English? So, and today I posted it, and some guys joined today and asked to switch in English. So let's try. I don't know how it will be, but I think it will be interesting experience for me and for them to see what we do in these streams. And today is already 50 stream on YouTube about FPGAs, so we did a lot of them. We're doing this almost every Saturday, and we started a few years ago doing this every Saturday. So if you would to join for future streams, please tell your friends, tell your colleagues that we do something interesting with VHDL Verilog every Saturday on YouTube. I will increase the font because Vivado font currently is very small. Give me a second, I will increase it to 25. Boom, boom, boom. Edition. Monte Carlo size. Okay. Okay. That's better, I think. No, sorry, I will start with VHDL and then we'll switch to Verilog. It's much simpler for me. Do not use Verilog, do not use VHDL, use Verilog. Do not set tabs as free spaces, set tabs as 4 spaces. So, for shifted free, we will need a few ports, as I described previously. Guys, did you understand? Did you understand what I mean? The steps which we will create and how it will work. So, if you if you misunderstood something, please let me know. I will try to explain again. But I think you will understand when we complete this task. Typically, if you will try to find some specific implementation of some specific describes of a double-dabble algorithm or shift add free algorithm, you will see that typically its description in the block diagram will be divided by few submodels like our shift registers, but typically it's represented as some specific table, I mean lookup table with some conversion of numbers. So since we are working with FPGAs, we have some it should be absolutely synchronous system, so because it will need shift every clock cycle, no, every bit of number should be shifted. So that's why I suggest to do this, divide to shift and add operations separately. The one advantage which could be here is that we will absolutely know, it will be absolutely deterministic how many cycles it will require to convert one binary to two digits, if we know a width of number, if know width of number. So you will see this also later. I will show you how it works. So we will need a shift signal. So we will need a ADD signal. We also will need AD signals will be is our input for shift register. Since our registers should be connected sequentially, we will need to go one bit. So here is a wire. So binary shift register here will be a number, and we will by a bit to bit shifting to this shift register. And here output will be digit here, and this will be just OQ. There will be output of one register and connected to input of next shift register. Give me, I will put it here, and this will be put it here. So ID, next what we will need OQ. It will be our output. And we will need also O digit. It will be out D logic vector. So this is all ports which we will need to implement this. Also we will need we will not use specific libraries like unsigned or numeric std, because we will do addition using plus operation with std logic. like plus binary number 1 1. So first of all, what we need to describe our the logic vector. Sorry, I forgot. 3 down to 0. So we will use only one process. It will be synchronous process with clock. With clock. So we will have synchronous reset. Okay. And else statement. So what I not present in architecture code. Of course, we will need the structure of our shift register. So it will be very simple shift register, which will is the logic vector 3 down to 0, which we will need to set to 0 when we will initialize it. So this is not used, this is useless for ASIC designs, but it's very helpful to FPGA designs to initialize in active state all signals, internal signals, which you will use in your design. So okay, so first of all, what we need to set if we have a reset signal, or it will be a clear signal from our FSM, we will need to reset it to 0. And here we should describe we should describe our shift registers. Actually, existing 3 types of describing shift registers, as you know. You could describe if one signal to other signal assignment. It's also very simple. DFF1 to DFF2, DFF2 to DFF3, etc., etc. You could use specific notation using how to say most significant bit of your shift register, and you could use how to say other part of this register. It's also could be found here. Give me shift. It was something here. Shift register styles. So it could be described. No, it's attributes. Yes, it's attributes. So here are the code examples, and you will see here some code of examples how to describe your shift registers. Exists some different types of describing of shift registers, as I told, using for loop, for example, using continuously assignment of signals of your shift registers, or you could use some specific other notation. So our designs will be very simple. So, and I will just create a very stupid description. So never do this. If you will work with it, never do like me. I will describe it like this. Second Control D. SR1, SR0. SR2 is SR1, and SR3 is SR2. So So that's well enough to describe our 4-stage shift register. That's very simple. Of course, you could use a for loop if you wish, but it's typically it's useful when you don't know what the width of your design will be. In this situation, in this current situation, we know that this will be absolutely determined number of registers in our shift register. So we described it, and we will do shifting when our E shift signal is equal to 1. And we will add 3 to and how to say reassign number of in which currently will be present in our shift register if EADD is equal to 1, and if this shift register contains number than more than 3, more than 4, yes, it's not recognized operation. So if it's more than 4, then we will need just assign to our shift register new value with addition to 3. So not recognized. Okay. Now it's okay. So this will be very simple. So I suppose you understood how it works. We have a shift register. If shift is equal to 1, we will shift our bits in our register. If we will have EADD, we will first of all check this is if content of our shift register is 4, is more than 4. It's then we will add 3 and assign this new value to the same shift register. So we will continuously add doing shifting and then add shift add, and this will be very simple implementation. So let's see how it looks in elaborated design. If what dialog is open? Settings dialog is open. Quite strange. Ah, yes, sorry, I forgot to close it. I zoomed the code, don't worry. So I suppose guys just think it's connecting not a long time ago, viewing from zero, from start. Okay, design is empty. Of course, I forgot assign output OQ and ODigit. So I forgot it. Okay, OQ will be the last bit of our shift register. It will be SR3, and digits and digit should be assigned to SR shift register. So whole all value which contains in our shift register should be assigned to digit output. So let's try to load it again. Where are you from, guys? So yes, we have something don't understandable here. Shift register, something multiplexer, comparison, additional. Okay, let's see how it looks in synthesis. Oh, why is synthesis so long? Okay. So what we have here, one register, second register, third register, and fourth register. Okay. 1, 2, 1, 2, 3. Yes, 4 registers and some around logic. Okay, so our module will contain 1, 2, 3, 4, 5 lookup tables and 4 registers. Okay, it's slightly small. So next, what we will need to describe is some chain of this shift at 3 registers. So I will create a new top-level module. It will be Double-Dabble. So I will put it here. Okay. For this module, we will need first of all describe the ports. Describe the ports. What ports we will need here? It will be port equal. It will be our top level wrapper for whole model. So it will be also will need reset signal. We also will need number in binary representation. So it's in this number should have. We will do some plus minus parameterizable module. So and we will use some parameters. So it will be C number which it will be our binary number. So I will need puts here generic statement because this is a parameter. Let's see, it will be, we will start from example from Wikipedia. From Wiki, it will be 8 bits. Thanks for subscribe. It will be just n 8 bits. So it will be parameterized. So and also we will need parameterized as a number of digits itself, number of decimal digits. Actually, somewhere in articles I found a formula which could, let's say, to help understand to help find how much digits will be after representation. So it's some not difficult formula. This is equation, but typically, actually I don't know. It's not how to say. It's not always, I suppose, recognize it correctly. So I need to floor or sale operations. So currently, for current implementation, I will not use this formula. You could investigate it by yourself in future, maybe for your future release. And I just will put a number of digits itself. So I will just put 3. It will be 3 digits. But you could try to use this formula to do parameterization based on only one parameter as a number of as the width of your binary number. Okay. Okay. Number we have. So we also will need start signal. This start signal we will use just to know that our new digit should be converted to digits. Our current number, new binary number, should be converted to digits. So it will be number in, start also will be in. Next signal what we will need is 4 digits. It will be just in a big vector of digits. So it will be std logic vector of number of digits multiplied by 4, because we have a 4 bit for every digits, -1 down to 0. So this vector will contain all digits. So if you will need to get any digits from this number, you could do this by slicing of this vector. What next? We will need a signal done to know when our conversion is complete. Okay. I think that's all. Clock reset, number start, digits, and done. Okay. So for our architecture, inside our architecture, what we need to put, we will create a FSM as a finite state machine, as I told you before, and this will be type state type 0, S1, S3, S4, S3, S4, S5. I don't know how much we will need, but I just put some sets of states for our finite state machine. Signal state type assigned to S0 during initialization of FPGA. Okay. Okay. We will do also shifting some much times. Okay. And this number, it should be the same as the number of widths of our binary number. So okay. So we will need some temporal variable to calculate how much shifts we already did, and stop our shifting and additional when this variable will be 0, when the signal will be 0. Let's talk, this will be natural type, and range will be as the width of our number. I will not do this. I will write as another as E number range. So that's simpler. And of course assign it to 0. So what we will also need, we will also need some internal signals, I suppose, the signal shift. Which we will assign in finite state machine. Also we will need signal ADD and I think currently is enough. So first of all, let's let's create this chain of shift registers. Oh, not much people in translation. It's said. So let's first of all create this chain. So we will use, as I told you before, generate statement. So for E in number of digits down to 0. Down to 1, I suppose. Generate and generate, and I forgot, seems I forgot to label. Yes. So here we will need to put our module shift ADD. Shift ADD. So it will be to use it inside VHDL, to using some specific components. Typically we use a component, a declared component here in architecture, but I prefer not use it. I prefer following indexes. Library work, it's a default library for VHDL projects, and use work.all. Shift add, and we will need put here behavioral. Let me change it to RTL. I don't like behavioral architecture naming. RTL. Okay, so now we'll need a port map of so here will be connect e clock. Here we will need connect some specific signal which should be clear signal. It's not reset from top level model. It's just be some local reset for shift registers. It should be signal clear. Okay, port map. So it should be clear signal. It will be common for all shift registers. It will be signal shift. It also will be common for all shift registers. Signal ADD also common. IQ. So now we will need to think how to connect our output to our input of shift register. So it will be shift register number 0. Will be 0 connected to 1 and connected to second. Okay, so we will need some specific signal also. Signal I will name it like from to signal. It will be std logic vector d digit to 0 down to so here will be from to. For example, if we have some shift registers, first 0 from I minus 1 from 2 from I minus 1 to I. So now we created some specific sets of registers. Okay, 0 connected, output of 0 shift register connected to first shift register input, to first shift register input, this first shift register input connected to second, etc. Okay, and the digits, it should be digits, it's a free, it's a 4 bits output signal, so it should be connected to digits. But what is the range of these digits? I multiply 4 0 0 3 then 4 7. Give me a second. 3 0 7 4. And what's the next will be 11 8. So common formula for this is minus 1 down 2 E multiply 4 E if E is minus 4 E if E equals 1, it will be 0 here, 0 here, and 3 here. If E equals 2, it will be 2 multiplied 4 8 minus 4 it's 4, and 8 minus 1 it's 7. Yes, okay, that's done. Perfect. So we just created some chain of shift registers. Okay. I saw. Yes, already. Great. It's recognized by Vivado, and they already inside our architecture. That's great. So now we need to create our finite state machine. Так, надо сделать. During reset signal we need to clear all signals, set them to 0. So state should be done at 0. Shift. BCD 0, A is 0. Okay, and it's clear also 0. Okay, next what we will need is describe our FSM. So case, we will use a case statement as usual for describing FSMs, and case when others state return 0. Guys, type something if you are still here. It will be interesting to see any comments in chat, if it's possible. Okay, when it's 0, so it will our initial state, and in this initial state we will need to wait start signal. So start signal will be our signal for launch our computation. So if is start is equal to 1, we will need go to state S1. So and also in this initial state, response. Привет, Саймон. Приятно, что ты хоть остался на трансляции. Чувствую, что все уже ушли. Что-то народ так мало совсем. Это жалко. А ты когда-нибудь пробовал сам вообще реализовать этот Double-Dabble? А что не совсем? Я не понял, про что ты говоришь, не совсем. Не совсем понятно вообще, что происходит. Если хотите, я еще могу объяснить на русском, как вообще, в чем вся идея состоит. Как это разбить, если непонятно было с самого начала, когда я пытался описать это на своем ломаном английском. Ну, надо тренироваться, конечно, на английском сложно говорить, на самом деле. Я так не сильно-то и привык к такому суждению. Так, значит, state вернуть 1. Собственно, что будет дальше? Вот теперь мы переходим к такому моменту, что в состоянии будет у нас S1 мы будем сдвигать, а в состоянии S2 мы будем выполнять суммирование. Собственно, идея очень простая. State. Ругается. Когда S1. Значит, мы что делаем? Мы делаем сигнал сдвига. Было бы здорово итоговый вариант кода прокомментировать на русском. Ну окей. Но он там, в принципе, простой, там комментировать особо нечего, он же реально простой. Но главная идея понять. Собственно, давайте я еще раз идею на русском скажу, может, тогда. У нас вот есть число, и число в двоичной форме у нас выглядит, собственно, вот так, да? Значит, и получается, чтобы его преобразовать вот в этот вот набор цифр, 2, 4, 3, например, нам нужно проходить через шаги сдвига и суммирования тройкой, если число больше 4. Собственно, и вот если в такой реализации, то алгоритм имеет недетерминированную задержку, то есть вы не знаете, сколько у вас будет именно сложение с тройкой. Это может быть там и 10, и 1, например, да, и вы не можете определить. И я в чем подумал, что было бы удобно реализовывать этот сдвиг, суммирование, сдвиг, суммирование, сдвиг, суммирование. То есть они идут последовательно, одна за одной, и, соответственно, задержка будет детерминирована, будет равна удвоенному количеству цифр в вашем числе. Да, то есть здесь 8 бит, значит, нам потребуется там 15-16 тактов для того, чтобы преобразовать полностью число. То есть это заранее известное количество будет. То есть не нужно ничего проверять. И, соответственно, число, которое будет суммироваться, оно не может быть больше, чем... Сколько там получалось у нас здесь? 7. Не может быть больше чем определенного количества. То есть никогда за рамки вот этого значения оно не выйдет. Ну, не вот это значение, то есть за рамки 4 бит оно не выйдет. И поэтому можем просто смело брать и складывать текущее значение с тройкой. То есть нет, у нас не будет такого перескока, что вот здесь такое число получилось, и старший бит ушел вот сюда. То есть такого, по-моему, не должно случаться. Я надеюсь. Вот, потому что мы каждый раз дополняем там до какого-то числа. Даже вот мы всегда подавали вот одни единицы, и все единицы у нас превратились вот во что там, в десятку там, или в девятку, например. И, собственно, вся идея состоит в том, чтобы разбить блок на вот такие вот маленькие сдвиговые регистры по 4 бита и выполнять последовательность сдвига суммирования. И это должно, по идее, работать. Думаю, понятно. Вот, здесь, собственно, что происходит? Здесь я сделал вот этот сдвиговый регистр. Соответственно, если сигнал сдвига, то выполняется сдвиг на один разряд. Если сигнал суммирования, то, соответственно, выполняется сложение, если число больше 4. И все. Здесь конечный автомат. Здесь я сделал просто generate. Это, получается, я сделал цепочку из этих сдвиговых регистров вот в этом модуле. Это получается там 1, 2, 3, 4, 5, 6. И сколько там будет сдвиговых регистров, зависит от количества цифр, которые будет в нашем двоичном числе, в нашем десятичном числе, в конечном, в итоговом. Вот. И здесь, конечно, это число надо брать для случая, когда все единицы двоичные. То есть у нас там 8-разрядный вектор, и сколько у нас цифр получится в максимально возможном варианте. I just describe, guys, in Russian how it works. Maybe not all of them understanding English language, sorry. I will switch again to English a bit later. Вот, и получается, что я сделал просто цепочку, и теперь я делаю, конечно, автомат, который эту цепочку будет управлять. Собственно, и все. Который будет формировать сдвиг и формировать суммирование. Собственно, вся идея. So we will continuously doing in this realization we will do continuously shift add. So and this will have one advantage. We will have we will know how much time it will require to convert digits, to convert a binary number to digits representation, to BCD, because here in Wikipedia, as you see, it's not determined how much additions will be in your number. Okay, it will be 10 and maybe 1. But if we will doing sequentially shift add, shift add, shift add, we will know that it will require twice number of cycles of widths of our binary number. So it will require t number widths multiplied by 2 clock cycles to convert binary representation number to digital representation. Okay, we will shift add, we will need assign add to 0. So, and we will need in this situation check how what next state will be. So first of all, we will need to understand how much digits, how much bits we already shift in our shift register from our initial binary number. So if k is equal number not number, it's oh, it's parameter named, it's c number widths. Okay, is k is equal c number of widths, this will require to set shift to 0. We will do not need I suppose to shift anymore. And state, no, we will need shift, I suppose. We will need shift state back to S2. Else, not S2, S3. Else, in other case, we will need do k as k plus 1 and go to state S2 and do a condition. Still not declarated? Ah, okay, I missed here. So this will be yeah, we'll set comment shift, and when S2 it will be add 3. Okay. So in this case, we will need to just set add to 1, shift to 0, and back to S1. State back S1. So here I suppose when we complete calculations, we will need to wait one shift, I suppose, but maybe it's not true. Let's see how it will work. And after we will complete our shifting, we will need we will go to state S3 and set signal done to done back as 1. Oh, set done to 1. We will need clear our shift register we will need clear our shift register. Okay, let's clear it in S0. Since we always clear in S0. Okay. We will not control it and clear he will return clear to 0. So our shift register will be always disabled until it's going start conversion. So odd on is 1, and here we need to don't signal going to 0. So also inactive state. I think yes, we missed okay, I missed one thing which I described previously in the beginning of the stream. So we will save binary number in specific shift register. So we will create one shift register which will save this binary number, and then when this will save our binary number when signal start will be equal to 1, and then this register will shift bits of this number to sets of shift registers for converting digits. Okay, so I will need to create more one shift register. Okay, it will be srec, for example. Logic vector so, and this will be range of our E number. Number range. Currently it will be 7 to 0. So now I will need to describe it. So for this case, I can't use this as description of shift registers, because I don't know how much digits will be, how much bits will be for our binary number. So we will create some parameterizable module, as I told. So we will need to create a new shift register with for loop statement. Okay. It will be the same way. So, do we need some reset signal? Здесь VHDL очень простой, здесь только для управления он используется как раз. Здесь автомат только для управления, без логики. И VHD потом сделаем варилог. Я обещал, что сделаем варилог. Do we need a reset signal? I think we do not need it. If start is equal, start is equal to 1, then and if so we will need to assign our binary number to srec. If signal start is 0, and if we will use a shift signal from which control our these modules, yes, for shifting, we also will shift the number. We will shift the number inside of this srec. So we will use the same signal as a clock enable. If shift is equal to 1, for I in So need to think how to convert it. So let's so this will be most significant bit going first. So this will be shift register from okay, let's check it in the simulation from no, it will not work. Number it's down to 0, down to 1. For E, see number of bits down to 1, loop and loop. So we will need srec I back return srec I minus 1. So and we will need connect srec 0. It's input. Srec 0 should be connected to no, not srec 0. It should be and last input 0 to 1, 1 to 0, okay. 0 to 1, 1 to second, second to third, third to fourth, okay. And the last and output of the srec should be connected to first. Oh, what's happening? Seems I forgot disable NVIDIA driver and it's again freeze my screen. Ugh. Fucking NVIDIA Quadro. So last input of last srec should be connected to first of this structure of chain. So our chain ID from 2 0 should be connected to srec the number widths. From 2 0. Okay, something like this. We have FSM, we have temporal shift register, which save our number, and we have chain of our digits. Okay, let's see how it's connected. Let's see first of all, is it synthesizable or not? Yes, NVIDIA sucks. It's terrible. I don't know why, but typically if NVIDIA Quadro tries to do something on my laptop, it's freeze all all what is possible. And freeze screen and okay, it's just very terrible. But it's useful when I'm rendering videos. I suppose it's used by Camtasia use NVIDIA Quadro, and every time I need to enable or disable it for stream. And for today I forgot to disable it. And now we see my mouse, or maybe in translation you see some freezes. So it's low resolution function. What's function? Ah, yes, sorry, here is a oh. Guys, did you ever try to implement this double-dabble algorithm in your designs or your DIYs? Or not? Why should do me a warning? Ah, of course, I forgot range. Ну давай, пока. Увидимся. In number width of I think I did a mistake here when connecting something last of first bits from shift register to this chain, but let's see how it works. And this is not correct. I will correct it again. What the fuck? Number H. Ah, -1 again. Forgot -1. So if it's will synthesized, we will just need create some simple test bench to check it if it works correctly or not. I hope this will not take a lot of time. Create a test bench. Okay, it's done. It's very good. So what is here? Shift registers, SR Q30, Q30. 0 is going to second. Second is going to third. Okay, looks it's correct. Okay, let's create a test bench. So will be this bench. Oh, I forgot, I saved it in the wrong place. So simulation sources, test bench. Okay, we will need library work. I just will copy it. So port is not required for this test bench. We will need just signals. Signal e clock. Hello. How to start with FPGA? Boris, are you on Russian language or you don't know Russian language? Ой. Boris, do you know, do you speak Russian or not? Ну отлично, тогда проще. How to start with FPGA? First of all, actually I don't know how to start with FPGA. I started with FPGA a long time ago. So typically you need, for example, download one of available IDEs. I prefer to use, for example, Vivado, or you could download the Quartus from Altera, because here in Russia we have some specific digital design school which is free for all and it's available for everyone, and the new semester of this school will start in September, so you could join to this school absolutely free. And this school, during education, this school it's continues, how to say, it starts in September and ends in April of next year, so it will be half of year of education with FPGAs, with Verilog, with Quartus, and with implementation of RISC-V, with functional verification of RISC-V, with coverages, test benches, synthesizable code. You will develop your own RISC-V processor with some sets of instructions, so it will be a good start point for you. If you would to read the books, I would recommend to you Harris and Harris, Harris and Harris. I don't know how to say it in English. So, and also digital synthesis from Yuri Panchel and Alexander Romanov book. So you could buy it on DMK Press, and if you put Prime, and if you put special promo code FPGA-systems.ru, you will give a 20% discount for this book. Now, of course, join to our Telegram channel, FPGA Systems. All links in description, and you could ask also there all necessary resources to be able to start with FPGAs. Signal reset, signal E number. I will create two constants, not constants. Да, пожалуйста. Прощайся, если что. Тут просто сегодня необычный стрим, тут ребят на английском попросили что-то провести. Я стараюсь что-то тыкаюсь на английском. Number of digits, it will be the logic vector. It will be our binary number. So also we will need start signal, digits, and done. Okay. Signal. I'll start digits. Okay. Okay, signal is start, and all signals we will set to 0. Digits, its output, or down its output. No need to set to 0. Here we need to set to 0. Okay, clock reset we set, number start digits, what also need to, that's all. I think that's all. So need to create a clock signal. So k return not k after k period divided by 2. So clock period I need to create it. It will be constant clock period. Its time, it will be 10 nanoseconds, for example. And yep, that's great. So now we need to first of all connect our Double-Dabble model to design under test is entity in library work, which names Double-Dabble with RTL architecture. Yes, it's again RTL, and here also RTL with RTL architecture, and port map. No, first of all, generic map. Generic map. So here in generic map should be these numbers. It's okay, and now port map. So in port map we will need just assign these inputs and outputs to internal test bench signals. Yes. Like this, and something like this. Not working. Okay, it should be clock signal, it should be reset signal, it should be number, starts and digits done. Remove this. Okay. Okay, so now we need to create some impact to our module. So we will use a simple process, and I will create just very something simple to be able to run a process. For this process. So first of all, we will need to wait a few clock cycles for reset before set reset. Before to no set reset, it's assign reset. So. Oh, again, freezing. What? Wait for. So I just assign a reset signal. Okay, now we need to assign a clock start signal. So let's wait also a few cycles. Let's, for example, 10 clock periods. Then is start is a we need to back as 1. So in number we will assign to example from Wikipedia. This number. So it should back to us 243. Okay, and we will need the assign start after clock cycle. Wait clock. Wait for clock period. Wait for LK period and start back to 0. So, and we will need to wait on. We will wait at on signal. Wait on. Done. But I don't remember what is the syntax for wait on. I don't. Ah, not idon, it's odon. Okay, so and then we could try to repeat again, but with something different number. Let's say it will be 111. Oh, let's say it will be 0 0 0 0 1 1 1 1. So let's see how it works. I think that's all. Simulation, behavioral simulation. Okay, errors. Switch to tickle console and see what's wrong here. Character is not element of type STDU logic. Where is it? Double-Dabble to be 50. What? Huh. Okay. So let's see, does it work? And I see it's not work. Okay, looks I did a mistake. Ах.
Следующий стрим английский для ВГашника, книги, курсы, тренажеры, советы.
Ох, у меня опять полез компьютер. Give me a second. Спасибо за сотку, дядя с большими усами. Очень приятно. Спасибо большое. Да что ты все лагаешь ужасно. Гребаная Nvidia. Fucking Nvidia. Свой. Actually, we already did some YouTube stream. It will be YouTube stream number 42, where we discussed in the FPGA books how to what you could learn and what you could buy. But it was for Russian language, so I don't sure that will be helpful for English guys. But it's if you would to see it, you could find it in a special playlist in our channel. So, well, I can't debug because my laptop is freeze. So it's yes, something incorrect. But why incorrect? Signal start, signal done. So let's check it. Let's start debug. The most interesting part of every FPGA development. So need to set states, A, shift and clear signals. Select from 2 is not integer pass. Reset, run again. Let's see what's happened. So clear signal is equal to 0 is equal to 1. So YSend number is F3. Okay, F3. So F3 is S7 rec. And so what we see let's see is how it's shifted. How it's shifted as it's shifted correctly. So here I should have 3, then I shift. If here will be 1 is 7. Yes, looks it's correct. So okay. And if I shift 1 2 3 0 0 1 1 1 Yes, it should be E7. E7, yes, it's working correct. Okay. Working correct. So we don't need it anymore. Number of digits, number of bits. So state is equal to S1. We need to shift and then we need to add. Okay, let's see what's happening here. S3. Clock, no reset. Add not. So here I suppose it's something wrong here. 1, 2, why 1, 2? Should be 3. Now it's the most terrible part of stream, it's try to find an error where and what's a mistake. On this I will need your help, guys. So shift register works okay, it works fine. We'll shift and sreg 0 from to 0. Zero connected, 0. Connected to 1. I need this instance. So I need this instance, let's see. Okay, it's here, shifted to 3. Why it's 6 again? Ah, it shifted to 6, it will be shifted and it will be 6. It should be 7. Why it's 6? Looks I did a mistake when connect some types of 0 to 3 and chain and the last number. I think I need to check again. Give me check. First of all, you know what I want to do. I want to connect srec 0 to 0 to see that it will contain the correct shifting. We'll do a correct shift. Okay. Let's see 0. Let's check. So where is my srec? Oh, looks I remove it. Srec. So I remove it. So here's the first shift. Something misunderstandable for me. After shift, it is 6. Yes, it's shifted by 1. Okay, it's shifting correctly. So, and this last bit should be connected to S1 from code. Yes. The digits 1. Oh, I think I did a mistake here. Maybe something. Number of digits 0. First digit will be 0 digit. Ugh. ID it's from to I. OQ will be I plus 1. E is 0. Yes, it should be correct. So what's the problem now? Problem is here. Yes, we'll start from 0, so it should be I plus 3 down to I multiply 4, so it will be correct. So, and the output is not changed yet. Where is the don't signal? Oh. Oh, what's happening was a don't signal. Thinking S3. Ah, was from S3. I forgot exit from S3. It okay, done is correct. Working now. So digits is still incorrect. Okay, let's check why it's happening. What's happening? I can't understand where I did a mistake. I still hope that I missed the connection of modules between each other. So I think I mistake here, something here in this equation. From 2, 0 should be connected to last number. In one moment, SR0 should contain a 7. But game freezes. Why it contains 6? I don't understand why it's 6. Ah, it's shift in other side. It's shift to left. It should shift to right. It's shift to right, but it needs to shift to left. So that's why I take a 6. So I think I missed here in this. But why? 0 need to connect it to 1. If it's 2, be 1. No, it's correct also. Ah. Oh no, not A. Not A. Two. Number which? Okay, let's see. No. So guys, any ideas why it's not works? Because I little bit confused for now why it's not works, and can't understand why it's 6 here. I suppose that it's shift to right, but it's need to shift to left. But from code I see it's shifted correctly. Where is it? SRX7. So 1 0 1 0. Oh, something wrong here. Oh. Start signal is here. F3 inside. Start. No, it's something. It's okay. For ones, two zeros, 2 1. Now it's 3 ones, 2 zeros, 1. No. 1 1. Shift. Oh, why it's shift again? It shouldn't shift. Okay, I think I did mistake here. If shift is 1, not. Oh. The one shift is 0. Something strange. I don't understand why this register shifts. So shift, okay. It should be here. Ah, okay. I think it's a problem with test bench. So give me a second. I will check one thing. Yes, possibly this problem. I just want to check one thing. Ох. That's strange. Okay, 1 3 1 3 6 9. Want to check what's the output of digits. So start loading. It will be 1 3 6 again 6. Why 6? I don't understand why it's I didn't change something, but it's not changed as I planned. Hmm. A shift clock is okay. Doing condition, but it shouldn't do. Ah, okay, it's already contains not contains. Oh, it's something terrible. Terrible to understand when your PC is not working as you expect. Oh. Очень последнее. Ой. Так. Ай. Блин. ОМГ, guys. ОМГ. I just forgot add rising edge. Yes, OMG, I just forgot rising edge, and it works on both rising clock edge and negative clock edge. So, and here I have 2 shifts instead of 1. So this is stupid mistake from my side. Sorry for this. It's really stupid. But it's happened sometimes on YouTube streams, so in life it's happened sometimes. Okay, here's our number 243. So, and I need just the limit number of shifts. Just need to leave it to when S3. I don't know, I don't understand why shift is still 1. So okay, let me check. State 0 when S3. When we go to S3, I need to, yes, disable shift. Set shift to 0. I think, and maybe tone signal should be also that stage. Yes, it's here. Okay, 243. Okay, it works. Okay, it's working now. So, and here working for now, and it's working for now. Start 0. Wait, hold on. Wait for the clock cycles. Number assign 0 to F. Okay, it's Y. Okay, I forgot here in this bench to reset. It's going to another stage, reset stage, so need to wait for done. And done signal should be, we do not need S3 stage. I think we will need only here. Shift goes to 0, down goes to 1, and we would go to state 0. Let's check it. So what we have here, yes, it 2, 3, but maybe we will need more one shift actually, because 1, 2, 3, 4, 5, 6, 7, 8. No. Okay, 8 is okay. And state to 0, and we will need to. Okay, that's okay. So 2, 3, 4. Okay, and next number which it's incorrect, I suppose. It's not 18. Number in second number is not 18. Okay, well, I need to check it. How it shifts again. So how it shifts again. So I sent. Oh, it's a the reset. Okay. Signal start 0FF, 0F number. So it's starting from 0, 0F, 1E, 3C, 7, 8, F0. difficult to check numbers, so maybe I need something. So what's the first digits? What's the first digit of this? Was 8. So if I have 1, I do not need, I will have 3. 3 plus 1 is 7. 7 plus 1 is A. 7 plus 3 is A. So I shift it, so will be 5. 1 plus. Oh, looks like I need more one shift. More one shift add. Huh. So 1 and should be 15, but it's take me 81. Ah, okay, 2, 3, 4. Ah, okay, it's just a wrong shift. We'll create one additional gain. We need to check. It's will be first digit. Will be 4 digits. Okay. Here's a 15, but it's add again. So I don't know. Shall I add again after? Shift and shift. Maybe we do not need the last addition. But why not? Let me check with another number. So it will be 0, 1. So what this will be? Here is a done signal. It's start signal. It's a done signal. Should be 97. Ah, yes, it's 79. Second digit. So suppose we do not need the last addition. So 27. But it's strange. No, it's incorrect. 243 will be here. And here is a number 79. And here's a 79 also. Yes, I do not need last addition. I do not need this. So if I do not need this number, I do not need this, so I need to shift to 0 and here set to -1 maybe. Okay, it's correct. So we need go to state free. Wait. Free. Okay. So what I have, done signal idiot. Oh, it's incorrect. Oh. Ah. So in last time we just need to shift and stop shifting when down signal is high. Copy this here. Yes, 79. Okay, 200. 243. Okay, we could check some test bench where I can just add numbers and see is it correct. So I will just signal. Okay. Signal temp pair, which will be natural. Zero two. Zero two. The number widths. Okay. So I need to integrate some так. Так, std vector. So let's check. Yeah. Where's the team P? Team P. Oh. Oh, come on. We killed Vivado, I think. So, that's all. Vivado crashed. Oh, anyway, it works. It works. Need to restart it again, I think. So I think we will not do this in Verilog today, because it's a bit terrible was that I mistaken rising clock edge and forgot type it in process and debugging. Spent a lot of time for this stupid typo. Yes, unfortunately this happens sometimes in real life or in stream, so it's very often easy to see how a complete code already. So you see this website, it's already works, it's great, but you don't know how much time guy who created this code spent, how much time he spent for creating this code. And sometimes it could be hours or days before it publishing. So run the behavioral simulation. And let's see TMP and what's the number here and the number here. Okay. So what I suggest to add some simple assertion, maybe when odd on is equal to 1 and 4-digit, then check, and the falling edge of clock, so check that number of the digits is equal to, for example, TMP variable. Let me check how I can do this. Come on, open. Now what's happening again? Why it's not working? Yes, first stream on English and it's really going to terrible. Very sad. I need to kill Vivado, I think. Okay. Let's try again. Oh. And I can't initialize the server though. What's happening today? Okay, finally. Finally, it somehow works. ATP. Here I put here. So great. So to check a process, how to create a certain HDL. Set and report. So maybe I could check like this. Says where is described the operation not equal. HDL. My mistake. Equal to 1. The clock. Still. But what I want to try to do, actually I don't know. I think it will be something stupid. Guess it will be something stupid. Why I do this? Impossible to check. Ugh. Game freezes. Okay, guys, I think we could done for today. I will push this source codes on GitHub, so this works fine. Suppose we just checked some numbers, and let me check with last number, which I would. It's all zeros. So something like this number, but it should be positive. So it will be -1. Check something. Some big number. Yes. Like this is 64 bytes. 64 width length. So number here. Check. So length of this digit is which is 64, and number of digits it's 19. So let's try to check it. It's 41. Will not use TMP variables. Just check this big number. Okay, it's again problem with. Give me restart, guys. I think it will be better. And this big number is correct, as you see. So okay, so I just check this big number with 64 bits, and it's all ones, except of most significant bit. So now it's, as you see, it's a correct number. If we check in calculator, this all ones. Oh, I missed one. How can I change it? Okay, here's the same number is displayed in the calculator. So this big number and this are the same. So that means that our model is correct. So my main mistake was that I forgot place rising edge in this process. During I'm trying to explain how something works, I forgot this typical mistake with rising edge clock. So and we spend a lot of time to fix it. And today is traffic difficulties with my laptop. But anyway, it works correctly now. I'm not sure that we need to continue with Verilog code for today, but I will push Verilog code separately in GitHub. So I suppose it will be done this today or tomorrow. So no problem. That's great, that works. So I hope you understood the idea. We just create some sets of shift registers, which is very simple. Just shift, just shift and add every time for every bit of binary number. Okay, guys, if you will have questions, please ask me in Telegram or find me in LinkedIn. It's not a problem. And if you will have some ideas for next YouTube streams, I will be able to see is it okay idea or not. For next stream, I suppose I will try to implement a Berlehamp-Massey algorithm, which could help us to find a linear shift back register structure based on its output. So we will get an output, and we'll try to implement it, and we'll try to find the formula which produce this interesting output, or we'll try to understand and find the structure of linear feedback shift register. So this is all for today. Thank you for your joining. See you in next streams. I hope next streams will be much more stable than this one. Okay, see you. Bye bye.